Welcome back to the deep dive. We are jumping into what feels like a pretty revolutionary moment in additive manufacturing, Bambu Lab.
Oh,
Well, they haven't just released a new printer.
no, it's a whole new second-generation platform, the H series. It's a big step.
It really is. And it started with the H2D rolling out, the dual-nozzle machine. Looked like a serious professional contender.
Exactly. But then, almost immediately, Bambu Lab announced the H2C. And that one, it's built around this radical tech called Vortek, an automatic hotend changer.
Okay, right. Let's try and unpack this for you listening. We've got these two very high-performance machines, H2D, H2C. And our mission today really is to get into that debate that just instantly sparked up. Did the H2C, with its whole zero waste thing, basically make the H2D obsolete before it even properly landed?
Or, yeah, is it more like they're specialized tools, serving different needs? That seems more likely, but we need to dig in.
Yeah, is it a generational leap that replaces the other, or just different tools for different jobs?
And it's not just about comparing spec sheets, right? This is about helping you figure out your priorities. Are you after the widest possible material range, that versatility?
Or is it all about efficiency? Minimizing cost, zero waste, especially for multicolor stuff. That choice really dictates which machine makes sense.
Absolutely. But before we get to that split, that core difference, we really need to understand the foundation they share.
Good point. Both the H2D and H2C are built on this same second-gen platform. And that platform itself is a huge upgrade from, say, the X1C or previous Bambu printers.
Oh, the performance standards are pretty immense. We're talking machines that can hit a maximum speed of 1,000 millimeters per second.
1,000 millimeters? That's proper production speed territory.
It is. And crucially, they handle those demanding engineering materials. Max nozzle temp is 350 degrees Celsius.
Okay, 350 C on the nozzle.
Well,
and you combine that with the actively heated chamber. What does that get up to, 65 C?
Yep, up to 65 degrees Celsius. And that active heating, it's really what separates these from, your typical consumer or prosumer models.
Why is that active heat so critical for those higher temp materials?
It's all about managing thermal stress. Think about materials like ABS, ASA, nylon, even polycarbonate blends. They shrink as they cool, without a heated chamber keeping everything stable.
You get warping, layers pulling apart, disaster.
Exactly. Instant failure, basically. That controlled environment, it prevents warping, ensures layers stick together properly. It's what guarantees you get professional-grade, reliable parts. These are meant to be like personal manufacturing centers.
Right, not just hobby machines. And the hardware pushing the filament, that's been upgraded too, hasn't it? The extruder?
Oh, yeah. The extruder is now driven by a PMSM servo motor.
A PMSM, okay, break that down. Permanent magnet synchronous motor. How's that different from a standard stepper?
It's a significant step up. PMSMs offer much higher torque, especially at the high speeds these machines run at. And the control is smoother, more precise micro-stepping. The net result, they're saying 67% more extrusion force compared to their older systems.
Wow, 67%. So that means better grip, better control, especially with maybe tougher filaments or when you're pushing a lot of plastic quickly.
Precisely. Better control over demanding or high-flow filaments. And speaking of control, you mentioned precision. There's an optional vision encoder.
Yeah, I saw that mentioned for some models. What's it actually do?
The vision encoder, it's kind of a nod towards serious industrial use. It provides closed-loop feedback. So the printer isn't just sending a command like move here.
It's checking that it actually did move there correctly.
So it confirms the physical movement happened as intended. For industrial applications, that means guaranteed dimensional accuracy, better quality control. It verifies the actual tool path.
Okay, so speed, power, precision. Now let's talk intelligence and safety. The sources mention this. Huge network of sensors, like 23 sensors and 3 cameras.
Yeah, it's pretty extensive. It sounds almost like overkill, but it's all about reliability and automation.
Less like a 3D printer, more like a small self-monitoring robot.
Kind of, because that sensor network enables things like advanced failure detection. It can spot those awful spaghetti failures almost instantly and stop the print.
Saves a lot of wasted filament and time.
Definitely. And it includes crucial safety stuff, too, like internal flame sensors. Peace of mind, really.
But the feature that really jumped out from the sources was this AI pre-flight check. That sounds like a real game changer for preventing user error.
It absolutely is. Think about the most common ways prints fail before they even start properly.
Like leaving a scraper on the bed or forgetting you swapped build plates.
Exactly. The visual system scans the chamber first, checks for debris, leftover prints, forgotten tools, anything that shouldn't be there.
Okay, that's smart.
And then it audits the hardware configuration, it looks at the build plate you've installed, confirms it matches the slicer settings. It's trying to catch those mismatches that lead to first-layer disasters.
Automated common sense, basically. Preventing those facepalm moments.
Pretty much.
Yeah.
Saves a ton of frustration and failed prints. So yeah, that shared second-gen platform, it sets a really high bar.
Okay, so that's the impressive foundation. Now let's get to that fork in the road. The H2D first, the dual-nozzle workhorse, it landed first. What's its core idea?
The H2D, you could think of it as the Swiss Army knife of the two. It's built for maximum functional range, maximum versatility.
And it does that with the dual nozzles, 2 independently heated nozzles on the print head.
Exactly. Similar, like we said, to systems from established players like Ultimaker. It's a proven approach for professional machines.
Right. And the power of having 2 nozzles. It comes down to materials, doesn't it? But wait, dual nozzles often mean calibration headaches. You mentioned medium complexity for the H2D. Is that calibration the main complexity factor?
That's definitely the main part of it, yeah. The medium rating really comes from needing to get those 2 nozzles perfectly aligned the X, Y, and Z offset. They have to act like one unit.
So they don't print slightly offset from each other.
Precisely. Bambu Lab seems to have put a lot of effort into automating that initial calibration as much as possible, because historically that's been the Achilles heel of dual-head printers.
Okay, assuming you get that calibration dialed in, what's the big win for the user?
Material breadth. The absolute killer app is using dedicated support material, either soluble stuff that just dissolves away in water or solvent.
Leaving perfect surfaces underneath.
Exactly. Or even just high-quality breakaway support that snaps off cleanly. This lets engineers print incredibly complex shapes, crazy overhangs, internal channels, things that are just impossible with single nozzle support structures.
Right. And you can also mix material properties in one print.
Absolutely.
Yeah.
That's huge for functional prototypes. Imagine printing a strong, rigid frame out of, say, PETG or even carbon fiber nylon.
And then printing flexible TPU gaskets or vibration dampeners right onto it in the same print job.
Exactly. All in one go. And that ability to directly feed flexible filaments like TPU through one of the nozzles, that's a major advantage over systems relying solely on a remote feeder like the AMS for everything.
Ah, good point. It also helps with multicolor printing, right? Even though it still needs to purge filament.
It does optimize it, yeah. Compared to older single nozzle systems using an AMS where every single color change requires a potentially big purge.
The infamous filament poop.
Right. With the H2D, you can assign, say, your most common color or maybe your support material to that second nozzle. This just reduces how often you need to do the full purge cycle associated with the AMS, speeding things up and cutting down waste compared to a purely AMS-based multicolor setup.
Okay, so the drawbacks are some purging still happens, even if it's less than it might be otherwise. And the 2 nozzles physically take up a bit more space, slightly reducing the maximum print volume compared to a single nozzle.
Correct. Minor trade-offs for the capability.
But the verdict seems clear then. If your priority is maximum material versatility, if you absolutely need reliable TPU printing or soluble supports for complex geometry, or you want to combine rigid and flexible materials in one part,
then the H2D is probably the one for you. It's geared towards engineers, designers, professionals focused on the function of the part, maybe more than just the absolute fastest multicolor output.
but a versatile workhorse. Got it. But, okay, the H2D tackles the material versatility problem, but like you said, there's still some waste, some purging time. And that brings us neatly to the H2C, the newcomer, the one that promised to basically eliminate the poop problem. This is the precise scalpel, the zero waste machine.
Yeah, the H2C introduces this system called Vortek. It's an automatic hotend changer. It's important to clarify that it swaps the whole hotend assembly, not like a full tool changer that could swap in a laser or a different kind of extruder.
Okay, hotend changer, Vortek. How many materials can it handle?
So the printhead itself keeps one hotend fixed and active, but then there's this docking station, like a carousel, that can hold and swap between up to 6 additional Vortek hotends.
6 plus the one on the head. So
Yeah.
7 total materials or colors available in a single print.
Exactly, 7 total.
Yeah.
Which is pretty substantial.
7 is great, but the really mind-bending part is how it works, right? This wireless power and data thing. Seriously, wireless power for a component that needs to get up to 350 degrees Celsius.
It sounds like science fiction, doesn't it?
Yeah.
But yeah, that's the breakthrough.
How does that even work? Is it like a tiny induction cooktop built into the print head dock?
That's actually a really good analogy. It is induction heating. When a Vortek hotend is docked in the active position, it's powered wirelessly through induction.
Okay.
And the temperature data gets sent back wirelessly, too. No physical data pins.
So getting rid of physical power and data connectors, that must make the hotend itself way simpler and lighter.
Massively simpler. They claim the swappable Vortek hotend assembly weighs only 10 grams.
10 grams, that's incredibly light.
It is. And it completely sidesteps the big problems. Early tool changers had bulky mechanisms, unreliable electrical contacts that wear out or get dirty. This wireless approach is elegant.
Okay, so the efficiency advantage must be the headline here, especially for anyone doing high-volume printing like print farms.
Absolutely. The #1 selling point is near zero waste, because you're swapping the entire hotend, melt zone included.
There's no need to push old filament out with new filament.
Exactly. You avoid almost all of that filament purging the poop. For a print farm, churning out hundreds of multicolor parts, the material cost savings could be enormous. And it simplifies waste handling.
And it's fast, too, swapping and heating up.
Pretty quick. They say heating a newly docked hotend takes only about 8 seconds. So the swap time isn't adding a huge overhead.
Zero waste, fast swaps. Sounds almost perfect. But there has to be a catch, right? A limitation. You hinted at material compatibility.
There is a pretty significant caveat, yes. And it connects right back to something we discussed earlier. The H2C's Vortek system, clever as it is. It still relies on the AMS, the automated material system, to feed the filament to the docking station where the hotends pick it up.
Ah, so the filament still has to make the journey through all the AMS Bowden tubes before it even gets near the hotend.
Precisely. And we know the AMS, while great for many standard materials, has known difficulties with certain filament types.
Specifically flexibles like TPU, and sometimes highly abrasive stuff can be tricky too.
Exactly those. So because the filament path includes the AMS, the H2C essentially inherits those same limitations. It struggles with reliably feeding TPU, and potentially some very abrasive filaments might cause accelerated wear in the AMS pathways.
So wait, the H2C gives you 7 slots for materials, zero waste, but only for materials that play nicely with the AMS system.
That's the trade-offs, yes. It dramatically optimizes multicolor printing and eliminates waste, but primarily for standard, relatively rigid, non-abrasive filaments like PLA, PETG, ABS, ASA, maybe some nylons. The things the AMS handles well.
Okay, so if the H2D is the versatile workhorse for tricky materials, the H2C is the clear choice if your absolute top priority is multicolor printing efficiency with standard materials.
Exactly. If you run a print farm selling multicolor models, or you just do a ton of aesthetic prints with lots of color swaps, and minimizing running costs and waste is paramount, the H2C is built for that specific job.
Maximum efficiency, but within the bounds of AMS-compatible materials.
That's the deal. High volume, structural or aesthetic parts, minimal waste.
Right, let's try and crystallize that different. Quick head-to-head on the key specs we've got.
Okay. Material capacity. H2C offers up to 7 simultaneous materials via Vortek.
While the H2D is technically 2 direct materials, but you can hook it up to the AMS for up to 16.
But using the AMS on the H2D still means relying on that purge tower system for those color changes, not zero waste.
Which brings us to waste generation. H2C, almost zero. H2D equals reduced purge tower, but still waste. That's a huge economic difference over time.
Massive. The material compatibility, maybe the biggest functional differentiator. H2C is limited by the AMS struggles with TPU, maybe some abrasives.
Whereas the H2D, with its direct feed path for those 2 nozzles, have high compatibility. It can handle TPU reliably, which is critical for many engineering applications.
Essential for functional parts, yeah. And finally, complexity. We said the H2D is medium complexity, mostly due to that initial dual nozzle calibration.
But the H2C, with the moving parts in the dock, the wireless power, the induction, that's rated high complexity, right? More potential failure points down the line, maybe.
Potentially, yes. More moving parts, cutting-edge tech. It inherently introduces more things that could need maintenance or adjustment over the long term compared to the simpler dual nozzle setup.
Okay. Let's talk brass tacks, price and availability. The H2D is out now or shipping soon.
The H2D is the one you can actually order. Base price around $1,999 USD, and the combo package with some extras is about $2,199.
And the H2C. Being the fancy new flagship with the Vortek, it's going to cost more.
Definitely. Its position as the flagship, current estimates put it somewhere between $2,500 and $2,900 USD.
And availability, people waiting for the zero waste dream.
They'll need patience. The projection right now is that the H2C won't start shipping until the end of 2025. So quite a wait.
Right. And Bambu Lab was pretty upfront about this, weren't they? Announcing the H2C early.
Yeah, it was actually commendable transparency. They announced the H2C was coming while launching the H2D, specifically so early H2D buyers wouldn't feel blindsided a few months later.
They also mentioned an upgrade path, H2D to H2C.
They did confirm an official upgrade pass will exist, but they were very clear. It's complex, a multi-hour job involving swapping out a lot of components. It's not just bolting on the Vortek dock.
And upgrading from the older H2S model?
They basically said, don't bother. Strongly advise against it. The cost and time involved would be prohibitive. It just wouldn't make sense compared to buying the H2C outright.
So the message is, think of the H2C as a distinct new machine, not really an upgrade in the simple sense.
Pretty much. It reinforces that these are different tools built on the same core platform.
Okay, so let's circle back to our original big question then. Does the H2C make the H2D obsolete?
Based on everything we've seen, our final assessment has to be a firm no. It really doesn't.
It complements the lineup, it doesn't replace it.
Exactly. The H2C is a highly specialized tool optimized for a very specific, albeit important, task. High-efficiency, zero-waste multicolor printing with standard materials.
While the H2D remains the champion for maximum functional range, it's still the go-to choice for professionals who prioritize broad material compatibility.
People who need reliable, soluble supports for complex engineering parts, or absolutely must print with flexibles like TPU frequently. The H2D serves that need directly.
So the H2C is for pure, high-volume efficiency addicts, mainly focused on multicolor using standard filaments where waste is a major cost factor.
Precisely. Print farms. People selling finished multicolor goods. The H2C is potentially transformative for their bottom line.
Yeah, that choice really does seem to boil down to the economics for many users, if you're running prints nonstop.
The material and time savings from the H2C's zero-waste Vortek system could genuinely pay back that higher initial purchase price relatively quickly, despite its material limitations. The filament savings alone could be huge.
That efficiency gain essentially subsidizes the machine over its lifetime.
That's the calculation potential buyers need to make, the upfront investment versus the ongoing operational savings. That defines which tool fits their specific production needs.
Which leaves us with that final thought, the question for you, the listener, to chew on. Are those material restrictions you get with the H2C being tied to the AMS compatibility a price worth paying for the revolutionary efficiency and near-zero waste that the wireless Vortek system offers, especially for your specific printing goals?
Yeah, take a hard look at your typical prints, maybe even your filament recycling bin or purge bucket right now. The answer to that trade-off calculation, that'll likely tell you exactly which of these specialized H-series machines makes the most sense for your workshop.
Excellent breakdown. Thanks for joining us for the deep dive. We'll catch you next time.